this video is to introduce to you another technique in solving inequalities as an alternative to graphical and substitution methods. This is very useful for calculus, especially when the algebra for the first derivative is too difficult to get the second derivative to determine whether or not the turning point is a minimum, maximum, or a horizontal point of inflection. Firstly, we consider an algebraic expression as having a parity of plus or minus depending on the value of x. So all the way back in year 8, you were probably asked to solve x plus 5 is greater than 0. First, we find the critical point, which is x is equal to minus 5. Clearly, everything to the right of x is equal to minus 5 is positive, and on the left, it is negative. And therefore, we can deduce that the solution to this inequality is x is greater than minus 5. Now, let's also consider the very simple equation, x minus 3 is less than 0. First, we plot that the critical point is x is equal to 3. And clearly, once again, to the right of x is equal to 3, the solution is positive, and to the left, it is clearly negative. And therefore, the solution to x minus 3 is less than 0 is x is less than 3. Now let's combine both of these. Let's solve x minus 3 times x plus 5 is greater than 0. Now the critical points are the same as before. X is equal to minus 5 and x is equal to 3. And this divides this into 3 regions. As you can see from here, x plus 5 is negative less than 5 as before. And x minus 3 is negative less than 3 and positive greater than 3. Now, we're going to start multiplying these both together to get x minus 3 times x plus 5. We find in the first region here, x is less than minus 5. Negative values given by x plus 5 and x minus 3 will give us a positive value, as negative times negative is positive, as you should know. Similarly, in the next region, x between minus 5 and 3, x plus 5 is positive and x minus 3 is negative. And therefore, multiplying a positive and negative value will give us a negative value here. Finally, in the third quadrant, x is greater than 3. Both x plus 5 and x minus 3 are positive, and therefore will give me a positive value, as positive times positive is positive. Consequently, the solution of x minus 3 times x minus 5 is greater than 0 are the regions that the positive values were given. Therefore, the union x is less than minus 5 with x is greater than 3. There is an important idea here. We can deduce from this that when this function crosses a critical point, the sign changes, as seen with this result here. See? Thus, we can say that the sign alternates between adjacent regions. For example, if we are asked to solve x minus 3 divided by x plus 5 is greater than 0, we must remember that this expression is not defined when x is equal to minus 5, as the denominator will equal to 0 and therefore the expression will be undefined. I can easily solve this as I am looking for the regions that are positive, and therefore I can use the solution to this expression to find the solution for this expression. And the results are the same. Similarly, in the next example, solve 1 on x minus 3 times x plus 5 is less than 0. We know that the whole solution will be negative when the denominator is negative in this case. Therefore, we take the answer from before over here, as the expression is negative between x is equal to minus 5 and 3. Now, I'm going to show you some exceptions to which the sign does not alternate when crossing the critical points. Let's consider x minus 1 squared is less than or equal to 0. When the expression is raised to an even power, the expression does not change over the critical point. Therefore, the only solution of this function is 1, as this will make the equation equal to 0 and therefore satisfy it. Thus, we can then deduce that even powers do not change the sign across the boundary point. Now, in the next example, let's solve x cubed times x plus 2 to the 4 is less than or equal to 0. Now in the next example, let's solve x cubed times x plus 2 to the 4 is less than or equal to 0. We find that the signs also do not change over the critical points. Let's first plot these critical points. When the expression is greater than 0, the value of x must be positive due to the odd power of x cubed. Therefore, the solution is x less than 0. However, x cannot equal to minus 2, as the expression will equal to 0, and this is not included in the expression. The next example is a very difficult one. Let's solve x times 2 minus x times 2x plus 3 squared, all on x minus 4 times x plus 5 is less than or equal to 0. First, we must declare every critical point. These are the values that will make the expression equal to 0 or make the denominator 0. These are minus 5, minus 3 on 2, 0, 2, and 4. Now we'll lay out a critical point table. First, we will substitute x greater than 4. When we do this, all the terms are positive except for 2 minus x, which is negative. This makes the whole expression negative. Similarly, if we substitute a value between 2 and 4, we will use the rule that the sign changes over critical point values. So this is a plus, and this is a minus, and this is a plus. However, when we get to x is equal to minus 3 on 2, the sign does not change, as the expression 2x plus 3 to this 2 is an even power. Therefore, this remains as a plus, and then crosses over the critical point x is equal to minus 5 to become negative once again. Therefore, we find that the solution is x is less than minus 5, x is between and equal to 0 and 2, and x is greater than 4. But remember to exclude the values where x is equal to minus 5 and x is equal to 4, as the denominator will equal to 0 and will be undefined. So that's the end of this video. I hope this method will be very useful for you and easy to understand. So thank you. Bye.